Welcome to the GMAT Strategy Podcast. You're here because you believe there's a better way to study for the GMAT, and so do we. We created the GMAT strategy to maximize your results and minimize your effort so you can get to the fun parts about business school and life as quickly as possible. My name is Isaac Puglia, and I've been teaching GMAT classes and tutoring privately for the GMAT for almost a decade, and I've achieved a 99th percentile score on the GMAT and helped thousands of students get into the business schools of their choice. I'm excited to be a part of your MBA journey since we all at TGS think our world can benefit from the best possible business leaders that we can find. If this show is bringing you value, please share it with your friends and family who are studying so that together we can make this process as easy and as painless as it can possibly be. Let's go.
Welcome to lesson 17 of GMAT Math Basics. Today we're going to talk about roots. Roots are very related to exponents, but they're different enough that they warrant a separate discussion. Let's hop into a quick quiz and talk about the questions that we're going to answer in this lesson. Question number 1, what is a root? Question number 2, what is a square root? Three, what is a cube root? Question 4, how do you write roots? How do you depict them visually? Question 5, what are fractional exponents and how do they work? Question 6, what rules of exponents also apply to roots? Let's start at the top. What is a root? A root is the inverse of an exponent. Let me explain what that means. If we multiply 2 times 2, we get 4. Last time we talked about how that's sometimes called squaring the number 2, multiplying it by itself. You could think about that as taking it to the second power or the second exponent of 2. That just means multiply 2 times itself, basically twice. And so we get 4. 2 times 2 equals 4. That's 2 squared. The simplest type of root is what's called the square root. A square root asks you to produce a number that if you squared it, it would yield 4. So if the test asks you for the square root of 4, it's asking you for a number that if you multiply by itself, you'll create the number 4. What number, if it was squared, would yield 4? Hopefully, you're thinking 2. So the square root of 4 is equal to 2. And 2 squared is equal to 4. So those are inverse operations. The square root is the inverse of squaring something. It's almost like unsquaring, if you want to think about it like that. I'm just going to repeat this. A square root asks you to find a number that if you multiplied that number by itself, it will produce the original number. And all roots work this way. Just like we can take any number to any exponent, we can ask for any root of a number. It just happens that the square root is the most common root that we talk about and the most common one tested on the GMAT. Technically, we could call the square root the second root, just like you could call squaring something taking it to the second power or the exponent of 2. Having said that, when we take something to the exponent of 2, it's almost always called squaring it. And the same thing is true of the square root. We could call it the second root, but it is almost always called the square root. Now, similar to exponents in our recent lesson, again, technically 2 to the second power is 2 to the exponent of 2, but we usually just call it squaring the number. What if we wanted the fourth root of a number, though? That's asking you to produce a number that, if taken to the fourth power, yields the number that we want the fourth root of. Let me elaborate on that because it can get a little technical. Let's talk about the fourth root of 16. Recall that taking a number to the fourth power means that we're multiplying that number times itself 4 times. That's what an exponent is. If you don't understand that concept, you might want to backtrack to the previous lesson and go deep or maybe even repeat some of the exponents material. But if you understand that concept, that taking a number to the 4th power means we're multiplying that number times itself 4 times, then you can start to think about the inverse of that process. So the inverse of that process is to ask what number, if I multiplied by itself 4 times, would produce 16. That's the 4th root of 16. What number, if I multiply by itself 4 times, would produce 16? That's what the 4th root of 16 is. Many times you can just guess and test until you figure out what that number is. For example, you can just start with 1. What's 1 times itself 4 times? Hopefully you're thinking, that's just 1, but 1 is a lot smaller than 16, so clearly the 4th root of 16 is not 1. If I multiply 1 by itself 4 times, I don't get 16. But what's 2 times itself 4 times? That's exactly 16. 2 times 2 is 4, times 2 again is 8, times 2 a 4th time equals 16. So this tactic of like benchmarking, just kind of guessing and testing with some numbers and multiplying them by themselves 4 times, that's actually remarkably effective. You would think it wouldn't work that well, but it actually does, because we don't have a calculator on the quant section. Now, the calculator we do get in the data insight section has limited functionality, so you're not just going to be able to press a button like you could on a computer calculator, potentially, and say, like, what's the 4th root of this number? You won't have that functionality. So that's why this benchmarking tactic is important. But what's even more important is understanding the concept. If I ask you what's the 4th root of 64, you'll want some kind of process for figuring that out. But what's even more important is understanding, what am I asking you to produce? That's what is the number that if I multiplied by itself 4 times, it would yield 64. Okay, that concept is really the important thing that I want you to take away from today's lesson. That's called the 4th root of a number. Once again, and sorry if I'm hammering this point too much, but I just want this to sink in. The most common type of root is the square root. That's asking for the number that if you squared it, also known as multiplying it by itself, would generate the number that we are taking the square root of. That's usually how that's said. The square root of 4 is 2. The square root of 16 is 4. The square root of 25 is 5. What number, if I squared it, or what number, if I multiplied it by itself, would yield 25? That's 5. Let's try a couple examples. Can you tell me what the square root of 36 is? That's 6. What I'm asking you there is, what number can I square or multiply by itself to create 36? Hopefully you're thinking 6, but you could have benchmarked it if you wanted to. You could have said, well, 2 times itself is 4, 3 times itself is 9, still not at 36 yet, but I'm getting closer. 4 times itself is 16, 5 times itself is 25, 6 times itself, lo and behold, is 36. Now, many of you might not have to do that for a number like 36, but if it's a number like 10,036, that benchmarking technique might be helpful. Second question, what's the square root of 49? What number can I multiply by itself to generate the number 49? Again, you could just benchmark. We just did 6 times 6 is 36. You can move up to 7 times 7. Hopefully you'll know that 7 times 7 is equal to 49. Those are the basics of roots and, in particular, square roots. Before we go on, it's a good time to mention that it's worth memorizing what are called quote-unquote perfect squares. And it's worth memorizing all the perfect squares from 1 to 20. A perfect square just means that you can multiply an integer by itself to generate the perfect square. For example, 1 is a perfect square because 1 times 1 is equal to 1. 4 is a perfect square because 2 times 2 is equal to 4. 9 is a perfect square because 3 times 3 is equal to 9. So basically what I'm recommending is that you memorize the squares of 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, all the way up to 20. So off the top of your head, on test day, you'll want to know what 14 squared is. You'll want to know what 15 squared is. You'll want to know what 8 squared is. You'll want to know what 19 squared is, and you'll want to know what 20 squared is. It's very, very helpful shortcuts on the exam because while the benchmarking thing does work, perhaps obviously it's a lot faster if you memorize the common ones in advance. It's pretty unusual to see perfect squares larger than 20 squared on the GMAT. Could happen, but let's just estimate and say you'd be prepared for 97% of perfect squares if you memorize the squares of 1 through 20. Which is just a side note, but I think you'll find it quite helpful. So again, that's roots and square roots. Let's move on to answering the question, what is the cube root? You might guess that the next most common root is the third root of a number. And you also might guess that that's called the cube root. The cube root of a number is asking you to find a number that if you raise it to the third power, meaning you cubed it, it would yield the number that you're looking for the cube root of. So if I say, what's the cube root of x? I'm looking for a number that if I multiplied it by itself, it would create x. For example, what's the cube root of 27? You want to search for a number that if you multiplied by itself 3 times, it would yield 27. We can use the benchmarking technique again, actually. 1 times 1 times 1 is just 1, so that's way too small. 2 times 2 times 2 is 8, so that's also still too small. But 3 times 3 times 3 is exactly 27. Now, it might take you a little bit longer than it just took me to do that math by hand. That's okay. The important thing is the concept. Benchmarking to figure out what number can I multiply by itself 3 times to generate 27. That's called finding the cube root of 27. Now, just like I recommended memorizing some perfect squares a moment ago, I also recommend that you memorize what are called perfect cubes. And I would recommend that you memorize the perfect cubes of 2, 3, 4, and 5. 2 cubed, 3 cubed, 4 cubed, and 5 cubed. You'll want to know those. After that, it's so rare to find other cubes that you just don't have to worry about it. So there's quite a bit less to memorize in terms of perfect cubes than there is for perfect squares. But that's basically what roots are. They're the inverse of an exponent. The second root, or square root, is the number that's squared to produce the number you're taking the square root of. The third root, or the cube root, is the number that if you cube it, produces the number you're taking the cube root of. The fourth root, fifth root, sixth root, etc., it's all the same. The sixth root is a number that if you multiplied by itself 6 times, aka took it to the exponent of 6, would yield the number that you're taking the sixth root of. So if you want the root of a number, you're looking for the thing you can multiply however many times that produces that number. Just to drive this point home, the square root of 10 squared is 10. 10 is the number that if I square it, would yield the number 10 squared. Sounds maybe a little silly to think about it that way, but sometimes it's helpful to think about it that way. The cube root of 10 cubed is 10. 10 is the number that if I multiply by itself 3 times, would yield 10 cubed. The fourth root of 10 to the fourth power is just 10. The fourth root of 10 to the fourth power is just 10. You can think of those as undoing an exponent, or simply the inverse of an exponent. 10 to the fourth says what number is equal to 10 times itself 4 times. The fourth root of 10 to the fourth is what number can you multiply by itself 4 times to yield 10 to the fourth. That's 10. Now that you understand what a root is, let's talk about how to draw roots or how to depict them visually. And there's 2 main ways that this will happen on the exam. The first way is what I like to call the check mark. It's basically the letter V, if you can imagine that, the letter V, but the right side of the V keeps going up to the top of the line, and then it goes straight across above the numbers that you're taking the root of. I call it the check mark way of writing it because it looks kind of like a check mark. If you imagine drawing the letter V and then extending the right side of the V up all the way to the top of the line, that's like a check mark symbol. If you're not sure what I'm talking about, you can web search heavy check mark emoji if you want to know what that looks like. But I guess if you're going to go through all that trouble, you might as well web search what is the square root symbol. But hopefully that helps the visualization process for those of you on the pure audio feed. Once you have that check mark, which is the V with the right part of the V extended all the way to the top of the line, then you just extend that top part of the line straight across, parallel to the bottom of the page, straight across the top of whatever you want to take the root of. So if I wanted to write the square root of 1,000, I would write a small v, and then I would write 1,000 right to the right of that with no space in between, and then I would extend the upper right part of the v to the top of the line that has 1,000, and then I would draw a straight line right across the top of the rest of the number 1,000. That would depict the square root of 1,000. I like to call it the check mark way of doing it. It looks kind of like a check mark. If we did the square root of 4, you draw V. Then you draw 4 right to the right of that with no space in between. Then you extend the upper right portion of the V, and then you draw a straight line right across the number 4. And wherever that straight line stops, that's when you're done taking the square root of that thing. Okay, that represents the square root when it's just the check mark by itself over a number. How do we represent the cube root or other roots besides the square root? It's the same symbol, but we're going to include a number in a very specific place. So again, you write the same check mark symbol, but you write a small little 3 for the cube root right above the top of the left side of the V. So we've got the V. We take the right side of the V and we extend it up. But on the left side of the V, we write a little 3 right above that. It's like the 3 gets kind of tucked into the V shape. When that 3 is there, that means the third root, or the cube root of whatever is under the top line that I talked about drawing before that covers everything you want to take the root of. This could be done with any root. For example, if you wanted the fourth root of a number, you just write a small 4 on top of the left side of the check mark. If you want the fifth root, you write a small 5 on top of the left side of the check mark. That's the first and probably most common way to write roots on the exam. Now, quick important note here, the right side of the check mark can extend over one number. It could extend over several numbers. Like if you're multiplying several things together, you can take the square root of the product of all those numbers being multiplied together, or it can even extend over whole operations. For example, if we wanted to write down the square root of x plus y, we would write our check mark to the left, then we would write xy right to the right of the check mark, and then we would extend the top right side of the check mark straight across to the right, parallel to the bottom of the page, so that it is on top of the entire expression x plus y. And then where that top line stops, that's the end of what you're taking the square root of. Another example, let's say we wanted to take the cube root of a times b. You would write your check mark and then write a times b right to the right of that with no space between the check mark and the a, and then extend the upper right part of the check mark straight and to the right, parallel to the bottom of the page, above a times b. That's the most common way to depict roots visually. So if you see that symbol, that check mark symbol, and then a little like roof over some stuff to the right of that, that's asking you to take the square root of whatever's under that roof. The second way to write roots is using fractional exponents. And all that means is in the superscript, which you heard me talk about last episode, which is like up and to the right of the number where we typically write the exponents, in that space, instead of an integer, you'll have a fraction. That's a fractional exponent. The best way to understand how fractional exponents work and how they represent roots, which they do, is to use the first rule of exponents, which you might remember is when multiplying by the same base, you want to add the exponents. Let's use that rule to help illustrate the concept of fractional exponents. Let's say we wanted to find the square root of 5 to the first power. Imagine 5 with a 1 written in the exponent. Recall that taking the square root of a number asks, what number can I multiply by itself to create 5 to the first power? Let's think about that in terms of exponents. If you had to multiply 5 to the something power, 5 to any power, times itself to produce 5 to the first. So you had to multiply 5 to some power, some exponent, and you had to multiply that times itself one time to produce 5 to the first power. What exponent would you use? That's not necessarily an easy question, but the answer is 5 to the 1/2 power. So think about that first rule of exponents. If I multiply 5 to the 1/2 power times 5 to the 1/2 power, meaning I'm multiplying 5 to the 1/2 power times itself, you imagine writing that out, you're multiplying by the same base. So what do you do with the exponents? Hopefully you're thinking you add those exponents together. And if I add 1/2 plus 1/2, I get 1. So the result of 5 to the 1/2 times 5 to the 1/2 is 5 to the first power. 5 to the 1/2 times 5 to the 1/2 is also a number that I can multiply by itself to yield 5 to the first, which is the same as the square root. I think that's one of the best ways to understand that 5 to the 1/2 power and the square root of 5 have the same value. Those represent the same number. They both represent the number that if I square them, i.e. multiply them by themselves, it will produce 5 to the first power. So the exam will expect you to understand that the square root of 5 and 5 to the 1/2 power are interchangeable. That's what I want you to take away from this lesson. 5 to the 1/2 power is the same as saying, what is the square root of 5, which is the same as saying, what number can I multiply by itself to create 5? Let's use a couple examples to drive this point home. What's the value of 16 to the 1/2 power? Hopefully you're thinking, that's the same as the square root of 16. What number can I multiply by itself to generate 16? Hopefully you're thinking 4. But if you're unsure, you can benchmark it. For example, what's 2 times 2? That's 4. That's a lot smaller than 16. What's 3 times 3? That's 9. Closer, but still too small. What's 4 times 4? That's exactly 16. Now, maybe it's obvious that it's better to remember that 16 is 4 times 4 or 4 squared, hence my previous recommendation of memorizing those perfect squares. But if you're stuck, go ahead and use the guess and test method. It works totally fine. Let's talk a little bit more about fractional exponents. Any idea how you could represent the cube root of a number as an exponent? The answer is taking a number to the 1/3 power. Let's talk about why that works, and I'm going to use that first rule of exponents again to try to connect the dots here. Recall that the cube root of a number asks you for a number that if you multiply by itself 3 times, yields the original number, or the number that you want to take the cube root of. Now, we calculated this very quickly earlier, but the cube root of 8 is equal to 2. I was using this as a benchmark. If I multiply 2 times itself 3 times, I get 8. So what's the cube root of 8? It's 2. So what exponent could I multiply by itself 3 times to generate 8 to the first power? Again, let's lean on this first rule of exponents. When I'm multiplying by the same base, I add the exponents. So if you imagine 8 to the 1/3 power times 8 to the 1/3 power times 8 to the 1/3 power, what would that yield? Hopefully you're thinking 1/3 plus 1/3 plus 1/3 is equal to 1. And hopefully that helps you see why 8 to the 1/3 power is the same value as the cube root of 8. It's what number can I multiply by itself 3 times to yield 8 to the first? The additional association that I want you to make there is 8 to the 1/3 power is equal to 2. because the cube root of 8 is 2. 2 cubed is equal to 8. Now, the specific numbers and specific examples are less important. The concepts are more important. Understanding, okay, a fractional exponent is the same as a root. And we'll get to how you can quickly discern what kind of root you're looking at based on the fraction. Let's hold off on that for a second, though. This concept of fractional exponents applies to any root. If you want to know what the 10th root of, let's say, number x is, that's asking you for a number that if you multiplied it by itself 10 times, it would create x. You can express that as a check mark with a 10 on the top of the left side of the v, and then the right side of the v up and to the right, extending over x, the letter. Or you can write that as x to the 1 over 10 power. That's fractional exponents. A quick final point here. All the same rules of exponents apply to roots. So I just used that first rule of exponent, which is when I'm multiplying by the same base, I add the exponents. I just use that first rule of exponents. But all the other rules of exponents apply to roots. And this is part of the reason that understanding fractional exponents is so valuable. It can make it easier to apply the rules of exponents that you hopefully already learned from the previous lesson. So here are a couple examples to help solidify this concept. What's 4 to the 1/2 power times 4 to the 3/4 power? So 4 to the 1/2 times 4 to the 3/4. Any idea how to figure out what that is? Let's talk through it. We're multiplying by the same base, and so we add the exponents. Just because they're fractions doesn't change that rule. When we're adding fractions, we want to get a common denominator. So let's turn 1/2 into 2 over 4. And I'm just going to assume you understand common denominators. If you don't, go back to lessons 3, 4, and 5 of this series. That'll help with common denominators and fractions. But let's say you understand that 1/2 and 2/4 are the same. And then we're going to add that to 3/4. 2/4 plus 3/4 is 5/4. So the answer to what is 4 to the 1/2 times 4 to the 3/4 is 4 to the 5/4 power. And again, we'll discuss what 4 to the 5/4 power means in a moment. Let's illustrate how some of the other exponent rules apply. What's 4 to the 3/4 power divided by 4 to the 1/2 power? Again, what's 4 to the 3/4 divided by 4 to the 1/2 power? It's very similar. We're dividing by the same base. And so we're going to subtract the exponents. 4 to the 3/4, you could think about it as minus 4 to the 2/4 is going to yield 4 to the 1/4, or the fourth root of the number 4. 4 to the 1/4 is the fourth root of the number 4. Now, the way I said that isn't technically accurate. We're only subtracting in the exponent. So if I have 4 to the 3/4 divided by 4 to the 2/4, I'm going to focus only on the exponent and think 3/4 minus 2/4. When I'm dividing by the same base, I subtract the exponents. That yields 1/4, so the result is going to be 4 to the 1/4. Another quick example of this. What's 4 to the 1/2 power to the 3rd power? Or 4 to the 1/2 power cubed. What is 4 to the 1/2 power cubed? If I'm taking a power to a power, you might remember that I multiply the exponents. 4 to the 1/2 to the 3rd would end up being 4 to the 3/2 power, because I take the exponents and I multiply them. 1/2 times 3 is 3 over 2. Now, let's finally, and sorry for the suspense here, pause and dive into what that means. What does it mean when we say 4 to the 3 over 2 power? Best way that I've come up with to think about this is that the denominator of a fractional exponent is the root. So the denominator of a fractional exponent is the root, and the numerator of the fractional exponent is the exponent. let me say more about what I mean there. So if I have 4 to the 1/2 power, think of the denominator of 1/2 as 2, that's the square root, and then think of the numerator of that fraction as 1, that's the exponent. There are 2 different ways you could do that. You could do 4 to the first power and then take the square root of that, or you could do square root of 4 and then take that to the first power. Either direction works with fractional exponents. So again, the denominator of the fractional exponent is the root, the numerator of the fractional exponent is the exponent. Let's use another example. Let's say we're going to do 27 to the 2/3 power. There's 2 ways to do that. You can do 27 to the second power, because the numerator of 2/3 is the exponent, and then you can find the cube root of that, because 3 in the denominator of 2/3 in the exponent is the root. Okay, you could also do it the other way, which is 27 to the 2/3 power means take the cube root of 27 and then square that result. Either way works. I can either square 27 first, then take the cube root, or I can take the cube root of 27 and then square it. Now, it's worth noting that on the exam, there's no calculator. So usually it's better to attempt the root first, because that's typically going to make the number smaller, and then do the exponent second. We'll do a quick example of this. Let's say you're on the GMAT and you see something like 64 to the 5/3 power, or 64 to the 5/3 in the exponent. In the exponent superscript up and to the right of 64, it's 5/3. Taking 64 to the 5th power first is going to yield a very, very, very big number, and that's going to be tough to compute by hand quickly. But if I start with the root first, and I think of 64 to the 1/3 power, then I can benchmark that if I need to, and figure out what number can I multiply by itself 3 times to yield 64. So like 2 times itself 3 times is 8, that's too small. 3 times itself 3 times is 27, that's too small. But 4 times itself 3 times, 4 times 4 times 4, that's exactly 64. So that could help me deduce on the exam that the cube root of 64 is 4. Now, obviously, it's better if you memorize it, hence, again, my earlier recommendation. But this still works. Now that I know that the cube root of 64 is 4, then I can just do 4 to the 5th power, and that might still be a challenge for some of you at this stage in your journey, but that's going to be way faster and easier by and large than 64 to the 5th power first, and then trying to take the cube root of that big number. So you could visualize it as breaking up 64 to the 5/3 power as 64 to the 1/3 power, and then brackets around that whole thing to the 5th power, taking 64 to the 1/3 power to the 5th power. I like that way of visualizing it. I think it can be good for preventing errors when you're calculating this stuff under time pressure. But ultimately, it's up to you. If you just want to memorize that the denominator of the fractional exponent is the root and the numerator of the fractional exponent is the exponent, that also works. That also works great. Okay, so that's fractional exponents in a nutshell. Definitely reach out to us if you have additional questions about that, or you're not sure how to practice. Now, let's quickly answer one more question here, which is what rules of exponents actually apply to roots? That's a bit of a trick question because I already told you, but it's all of them. Every single rule of exponents applies equally well to roots because roots can all be expressed as fractional exponents. Now, there's one more note about that. Something that's also similar to exponents with roots is that when you're adding and subtracting roots, so if I was doing square root of 3 plus square root of 5, for example, those rules of exponents will not work. And hopefully you remember from the previous episode that when you're adding and subtracting exponent terms, you cannot use the rules by and large. And so it's best to factor out a common term instead. That's also true of roots. So if you have square root of 3 plus square root of 5, you're either going to want to estimate that in the middle of the GMAT, just try to find a couple numbers by benchmarking that are close. Or if there's something you can factor out of both terms, ideally you would do that. But there's no common factors of square root of 3 and square root of 5. Okay. Similarly, when you're multiplying or dividing roots, all the rules apply. All the rules of exponents apply, just like when you're multiplying and dividing exponents, all the rules of exponents apply in that situation. So, real quick example of this. Let's say I had square root of 3 times square root of 5 plus the square root of 3 times 7. So square root of 3 times square root of 5 plus the square root of 3 times square root of 7. That's a situation where I could factor out a common term. You'll note that the square root of 3 divides both of those terms. And you might recall that pulling out a common factor, when I do that, I write square root of 3 outside a set of parentheses, and then within that set of parentheses, I'll have the square root of 5 plus 7. Now, at that point, again, depending on what the question's asking you to do, you might have to estimate, or the answer to that question might just be square root of 3 times parentheses square root of 5 plus 7. Both could be possible on the GMAT. That's just an example of factoring out a root. Hopefully that's sounding very, very, very familiar from the previous lesson. If it's not, you might want to go back to that and allow me to help you work through how to factor out common terms when you're doing exponent operations. And then you might want to return to this lesson and make sure that you can apply that to roots. That's pretty much everything that you'll want to know about the basics of roots on the GMAT. There's plenty of other advanced strategies, but we'll leave those for another time. Once again, if you are in a pinch and you want some practice questions, you can ask any large language model or any generative AI tool of your choice to produce 10 root-based questions that would help you raise your GMAT score, or whatever version of that prompt that you want. You can ask, hey, can you help me out with how to apply root rules, or can you help me understand fractional exponents better on the GMAT? In the meantime, if you're struggling to see progress with your current study plan, or you feel like you're not progressing as fast as you'd like to, you're welcome to book a call with us, and we'll be happy to help you out with a plan to accelerate your progress. If you're also interested in working with us directly and understanding what that might look like, we're happy to explain that as well. If that sounds good, or you'd like to learn more before you decide to book a call with us, just head to our website, thegmatstrategy.com, which is linked in the description of this content, and check out our free video on how to reach your dream GMAT score in half the normal time. That'll get you used to our approach and how we like to do things differently. And if at that point you're like, yeah, I'm not interested in this, no big deal. But if at that point you're interested and you're like, I'd like to learn more, or I'd just like to get a little bit of free help live, then there should be a direct link to book a call and speak to one of my teammates who's going to be more than happy to help you out. If you have other thoughts or questions, or you're confused about any of this, feel free to send us a DM at the GMAT Strategy on current social platforms, and we'll do our absolute best to help you out. As always, my greatest hope is that this material will make your studies as easy and as painless as they can possibly be. If you'd like more tips and strategies for optimizing your performance on the exam, like I mentioned, please head to thegmatstrategy.com and let us know how we can help further. In the meantime, this is a regular show, so please subscribe and please stay positive and stay consistent with your studies. I'll talk to you all soon.